Okay, so what was our last thing in the previous class? So we were trying to derive the Cobb-Douglas from the Sparse max, and we obtained this new demand function, which has some interesting features, right? Main feature is that now, so the budget shares is no longer constant. You actually have mistakes because of the misperception, right? So, but again, this is a little bit too general. So we want to understand what is misperception and how people create their perceived price, right? Right now, the perceived price is too general. Do you agree with me, right? It's too general. So now we need to do something. And so I'm going to propose this model by Gavex, which is basically an weighted average of true prices, and then the other component being a default price. So I'm going to explain a second more formally what this can mean, but now intuitively, right? So you're going to a supermarket, and then what is the default price? So the default price is kind of the price that you have in your mind before going to shopping. So that's the zero cost information you already have. So if you go to a supermarket and you're thinking of bread, so more or less you know that it's around $1, right? So okay, that's it, right? So you don't know exactly the price, but you know the value more or less. So when you're going to buy a coffee in a Starbucks, okay, so more or less you know the average value. So that's kind of the idea. Now, so the default price is information you already have access, free of charge. And now the price, the actual price, that's the real state of the world. And you have to use the current information you have, the prior, the default, and then kind of update it given the information you gather from the world. So in the end, you're gonna see this is not necessarily Bayesian because this model is reduced form, but this is compatible with Bayesianism. So we're gonna do then an example of Bayesianism that gives you this kind of model. But right now, this model is just given. So this is a decision Gavex did. This is a modeling decision. Gavex says, look, you have some default and you have the true price. What is going to be the psychological price? It's going to be a weighted average of that. With respect to what weights this ML. So ML is going to be a number between 0 and 1. When it's 1, you're rational. When it's 0, you are this agent that doesn't care about prices. You just go by mind, right? Or pick whatever you want and then keep going. Got it? So everyone agrees, gets the model because here is not approved.
It's like so when M1 is 0, you have less attention. 1, you have more attention.
Yeah, remember the default price is not changing, right? So the idea is that, for instance, if you go like you come many times to the same place, right? Then you always think is $1, right? So we're not thinking dynamics in here. So you go, let's say, in a month 4 times to the supermarket. So during that month, you don't expect price of bread to change, right? Except there is some weird thing, some shock. So within a month, you imagine the default price is always $1, right? So then you go there, and then sometimes you have promotions, sometimes you have some weird stuff with the cost of wheat, right? And therefore the price is fluctuating, okay? But you don't care. So the fully inattentive guy will always think it's $1 and then adjust whatever at the counter, okay? So this is the extreme of 0, m equal to 0. The other extreme is, of course, the rational guy, which if you think about it is also very extreme because m equal to 1 means that, you know, when I go to the supermarket and they did a promotion and did 99 cents, right? I'm going to notice it, even if it's 1 cent. Or maybe they increased, which is more likely, they changed a bit the price because the store decided to charge an additional premium just because they located the loaf of bread in a better shelf. So they add, 2 cents. Are you going to notice that? Not really, right? I think there was a famous scam of someone doing 1 cent extra in every transaction and he got rich. You know, nobody notices 1 cent, right? So this is kind of the, most people are not going to notice it. And yeah, we can argue that also about asymmetries of attention. So, this is a very complex topic, but this is the first model we're going to study. So that's the model. Utilities are the same, right, as before. So the new thing we're adding is this psychological price. So remember the object in the Gavex model that we studied is this PS. So now PS is now a function of true price, right? And then this parameter. PLD is a parameter. It's not changing as prices change, right? It's fixed. And then M is also a parameter, right? Here is not changing. So this first model we're going to study just inattentive. So the agent is not actively updating the attention they pay. They already kind of decided and they're going to go with it, okay? Then we're going to think of situations where M changes, right? But right now we're not going to endogenize M. So right now M is exogenous, right? Got it. So now, annotation step, capital M is a matrix of size L times L, where the diagonal entries are the M values, okay? So it's just a matrix of L times L. All of the diagonals are 0. In diagonal are the M's from 1 to capital M. How many M's do I have? I have good specific M's, okay? Now, another thing I want you to notice before going to the result is that let's count parameters in the Cobb-Douglas. So say you have two goods. How many parameters do I have in the rational Cobb-Douglas? 2, right? Alpha 1, alpha 2. That's it. And now, how many parameters do I get in the Cobb-Douglas with the Cavex model? So can Zach, for instance, tell me?
No, sorry, I don't know that.
No, just focus on the screen, right?
Yeah.
Then let's count parameters, right? So according to this model here that you see in the bottom of the screen, right? So you have how many new parameters? You have ML. How many of them?
2 or 1?
No, one per good, right?
Okay.
So you have L goods.
Okay.
In this case, 2. Okay, 2 more. And then also the PD is also a new parameter. So you have is a vector of size 2, right? So it's 2 more. So it's 4 plus the alphas, right? Alpha 1, alpha 2. So in total, 6 parameters. Okay. So in this model, we went from a rational model of 2 parameters to a model of how many? 6. Okay. So this is a way more flexible model, right? Now, the next question would be: so is this too flexible? Maybe, right? Is everything goes? So we're gonna answer that next, right? So how do I know if everything goes or not? So one way to do it, at least in this world where everything is differentiable and nice, is by studying the Zlotsky matrix, right? Okay, so the Zlotsky matrix, we already know what it is the corrected matrix of substitution, right, with the income effects. So what are the properties of the rational Zlotsky matrix? So we know it's symmetric, negative semi-definite, and has some singularity properties, okay? So, for instance, negative semi-definite, I might remind you that implies that it's the weak axiom, right? And the compensate law of demand. You also know that the symmetry has to do with the guard, the SAR. And then finally, this singularity in prices has to do with the lack of money illusion, right? Now, this model, of course, is going to be different from rationality. So how different, okay? And what I'm going to prove is this. I'm going to prove that if I take the Zlotsky matrix of the Gavex demand, okay, then this is going to be equal to the rational one multiplied by this diagonal matrix, okay? So I'm going to see this in a second. I'm going to send you actually as a problem set doing this for the Cobb-Douglas model. But one example is before going all the way to I'm going to give you a parametric example. So imagine the Cobb-Douglas.
Diagonal matrix is the M, right? I think.
Yeah. So let me give you this example with the Cobb-Douglas. So the Cobb-Douglas Zlotsky matrix, right? I'm not going to write all the entries just because I want to do it fast. But imagine these are the Cobb-Douglas entries, right? Okay. And then what is the diagonal matrix that I'm telling you? So this is the rational one, right? So now if I compute the Gavex, that is the Cobb-Douglas, and then PS. Remember, this also depends on the psychological price, right? And I evaluate the PS actually in the default price. So basically this, as we can see in the result, P is equal to PD. So in other words, let me do it like this. In our model with the M, it means that the price is just the default price always, right? So this is a local analysis around PD, what you remember. And so this will be this matrix, multiply it by the following matrix. M1, M2. So, okay, so one example is, imagine, for instance, that the consumer is fully inattentive to good 2, right?
M2 will be 0, right? Yeah.
Yeah. So then what does this matrix gonna look like? I'm just gonna write down the result. So this is gonna kill, if this is 0, right? If I multiply this entry by entry, it means that this second column disappears, right? Okay. So in particular, you're not gonna get symmetry anymore, right? As simple as that. And then you're not gonna get negative semi-definiteness and so on. So all these properties are lost easily. So you will do the full derivation if you want, but this is telling you that this is generic for any model, right? So that's the cool thing. So it's not only for the Cobb-Douglas. Now, I want to realize under what special cases the Zlowski matrix is still symmetric and negative semi-definite. At least symmetric. Only let's think about symmetry. Under what
M equals 1.
properties? Sorry? M is equal to 1? Someone said that?
Yeah.
Yeah,
That's what
perfect, excellent. Okay, but what else? So what other case still works?
You have a M1 equals M2, would that keep it symmetric?
Exactly, so M1 is equal to M2. Who was that?
That was Evan.
Okay, so it's really cool that that case is actually very interesting, because that means that as long as inattention in this model, this is a special case, right, is the same across the two goods, then your behavior is still rational. So let's try to think about that, okay? So if you pay the same attention to changes in two goods, right, then basically it means, right, that there is no distortion in the relative prices, right? Do you see? So in a way, you're still reacting like rational, you see? So of course, it's gonna be, in the end, a different demand, but you still behave like rational. So you still are, so if I see your data and you don't have, you have symmetric attention, then I can never tell you apart from a rational guy. That's the bottom line. So that's the cool thing about this Zlowski matrix, because I know that the guys that have homogeneous inattention to everyone, they look like rational. So let's think. So let's think of the special case when M1 and M2 is equal to 0. Okay. So then what happens? What is the agent doing? So just describe what they do. So they have a bunch of they go many times to the market, and every time they think is the same price, right? So what they do is basically they have a fixed budget rule, right? So whatever income they have in the particular trip to the market, they divide it by the psychological price, which is the default, and then they always spend that fraction, irrespective of the prices, right? You see, so they behave almost like a Cobb-Douglas, and so they're gonna look rational, right? Another case is, so this is an interesting case, because when you're fully inattentive to everything, you also look rational, okay? Bottom line. So the only cases where you don't look rational is when inattention is very heterogeneous across goods. So the more heterogeneous, the more asymmetric you are, so M1 and M2 are very different, then you look more irrational to me, okay? In the sense that your Zlowski metric is going to behave very weird. Okay, so now, is this good or bad? What do you think?
I just have a question based on that. Let's say, like, wouldn't the, like, if you prefer a good over another one, reflect how attentive you are to prices or not of that good?
Okay, so Eduardo is asking something about attention and the relation to preferences, right? So in this model, the one that we're studying at this particular subsection, is a model of exogenous attention. So attention was somehow determined, right, before, and then maybe with good reason, right? But you are not thinking it every time you go to the supermarket within a month. Maybe you revise attention after a month, right? But within the month, I'm thinking, and the time you go to the supermarket, you are not revising attention. So attention is already given. Now, that's the answer within the model. Now, a small footnote for the answer in data. So I have a paper with a co-author, Nikolai Ryabov. It's a working paper, still not published. So take it within that dimension. But then we showed that these parameters in the GAVX model, they relate to, to basically how variable the price is, for instance. So if the price is changing a lot, then you pay more attention to it. We're going to see also something of that at the end of the class. So there are reasons that can explain why attention changes. But right now, at this stage, attention. Okay, so it doesn't have, it's fixed, so it's independent, right? Because it's okay. Okay, so right now let's prove it, why this happens. And the thing I want you to realize is that this relation does not hold for any price, right? It's only when price is equal to the default. So this is only very local analysis. It's kind of looking at this point where price coincides with the default price, then this happens, right? But let's prove it. So I have the GAVX model. So wait, right? So there is something I didn't in class. So sorry about that proposition. I think it's a very simple group. So let's do that before. So if I imagine I have a rational model, demand, which is, for instance, linear. Okay. So it's pretty good. Okay, so having some issues with echo. So let me check. So never having issues with me because the chat room is hard to see. But I'm going to check right now on the issue. Okay, so now is the echo better? No? Is that?
Not yet, Victor. Still echo.
Now, what about this microphone?
This sounds better to me.
Okay.
Yeah.
Let me check. Okay, let me check. Let me know. Just open your mic and tell me. Okay. If it's, then I'm gonna try other stuff. Okay. So the one remember we did a sparse max. So one question would be, can we simplify and instead of doing every time the sparse max optimization, can we just get a Cobb-Douglas, for instance, and then just transform it to the GAVX? So the answer is yes, I can do that whenever my demand is, for instance, linear in income. Okay. So examples of linear in income, the Cobb-Douglas, the constant elasticity of substitution, the CES. So many models that we use every day are constant on income. So think about the Cobb-Douglas, right? So the example of the Cobb-Douglas is, of course, that originally it has alpha of W. So it's linear on income, okay? So W is not to the square, in other words, right? So W is there entering linearly. So all these are covered, and in particular is a big family. So that's the point. Now, what is the benefit of this proposition? Is telling you, you don't need to solve the GAVX model every time. Sometimes you just can plug in within the rational, making some substitutions, okay? That's a cool thing. So imagine this XR, rational demand, is linear. Now, right, this means that we have that because of linearity, you can write it as XR, the rational model, evaluated at income 1, multiplied times income. Do you agree? linearity, right? That's the definition of linearity. Now, we know that if I multiply prices times the rational evaluated at PS, the psychological price, I will need a corrected income, right? W prime, so it's not the original income, such that I hit the true income. So because I have the wrong price, I have to have the wrong income, right, in the rational one. So my objective is gonna find this W prime. So W prime right now is defined as the unknown, okay? So W prime is the unknown.
W prime is less than W, right? It makes
Yeah, we're gonna see what is exactly, right? But yeah, I think so. That the intuition is correct. But let me give you the actual expression. So then I multiply P times XR evaluated at 1, right? Times W prime. That's the key of the linearity, right? I can take out the unknown. And then I just solve it by W prime. And now I get W divided by the inner product of prices with a rational model evaluated at income 1. So yeah, so in particular, what I want you to notice is that if I go to the Cobb-Douglas, right? And then instead of doing the sparse max, what can I do? So I can just take, so let me copy this thing here. I can also use proposition 9, the proposition above, right? And compute the sparse max Cobb-Douglas. So in particular, I can actually compute this corrected income, right? Which is equal to true income divided by the inner product P1, right? Times what? Times 1, income 1, right? With alpha, because that's the Cobb-Douglas. P1S. This is for alpha 1, of course. And then the same thing for P2. Okay, so this is the corrected income. Then the Gavex model is equal to the pretty much alpha W prime P, here is for good L, for good 1, P1S. So then I replace it and then it's back to what I obtained before, right? So I kind of saved myself the steps of doing the optimization. Got it? So I obtained the same thing. So again, that's one nice feature of the Gavex model, because you can actually, without optimizing every time, you can just take demands that we know from the rational case and make them now the Gavex model, okay? Good. Now, with that intuition,
I'm still a little bit confused about the W prime, how you got it, the derivation of W prime there.
okay, so it's very simple, in fact.
Okay.
So remember that what we want to do is solve this equation.
Mm-hmm.
I want pretty much the corrected income
Mm-hmm.
inside the rational demand, given the wrong prices, that multiplied by the true prices are equal to the actual income, okay?
So we are making a system to solve this kind of. Okay.
It's just one equation.
Okay.
It's just one equation. And then the key is that I plug in the property that is linear in income, right?
Mm-hmm. Mm-hmm.
So that means that instead of doing W prime inside, which may be highly linear, non-linear, whatever, I know it's for sure linear, so it's just XR PS1 W prime.
Mm-hmm. Okay.
And then because it's positive, I just solve for W prime. It's a scalar, right?
Right. Okay.
W divided by the inner product of P XR PS1. So this index that I show you in the case of the Cobb-Douglas is really this index.
Okay. Oh, okay. 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 Yeah.
So my point is that, for instance, take a CES. So remember you did this in the summer, so you solved the demand for the CES. It's kind of messy, right? A lot of computations and so on. So imagine you have to do it now for the Cobb-Douglas, for the sparse max of the CS. So it's gonna be maybe too complicated. Well, it's easy, it's doable, but it's still a lot of work. So instead of doing that, you just recognize that the CES is linear in income, right? So you can just take this thing and use it to derive the GAVEX model with the CS. So many models are linear in income, so you can just use this, okay? So it makes it easy to use. And also the good thing about that proof is that also gives you this intuition that, well, in the end, the GAVEX model is doing is because you have the wrong prices, then you also have to have a corrected income, right? Okay. So it's a second way to see this issue of the lambda S, okay? The lambda S is like the Lagrangian, it's the marginal utility of income. So in a way, it is related to this corrected income, okay? So now we're gonna prove this property of the Zlowski matrix. We're gonna do it generically. So let's just start with a generic GAVEX demand. And you have XR PLD plus M1, this is for a given good, right? So this should be ML. PL minus PD, so this is just rearranging terms, right? It's the same model. If you multiply it, you're gonna get the same model as before. And then here you have this corrected income, right? This is the correction income as before. Now this corrected income, the good thing is that I'm not gonna make any assumption about what it looks like. I just know it's a function of prices and the default prices, okay? That's the only thing I know.
Sorry, so there's a comma right after P1 PLD there. Is it?
Yeah, it's just because you have two arguments, right? So this is the price argument.
Oh, I mean within that, the right before the plus.
Here?
Yeah, that one. Oh, okay.
Yeah. So so this is the model, the one you saw before, right? So you have the wrong price and the correction income. Okay. Now, I want to derive this function in terms of prices and income. So let's derive it with respect to price L, good L. So now I just do a lot of chain rules. So take the rational demand and derive with respect to PL. So where is P is inside this argument and inside the second argument. So the P is actually entering the argument 1 and argument 2 because W prime also depends on price. So the first argument is going to be a partial with respect to PL of XR with respect to the prices, right? And then this is equal to, by the chain rule times ML because prices here, right, are multiplied by ML. And then prices also enter this part. So is the partial with respect to W, second argument of this function that I don't know, but the partial with respect to W prime PL, okay? So good. Now I want to pin down this derivative just from the Walras law, right? So I once again write this thing that I wrote before, and this is the Walras law. So for the wrong prices and the corrected income, this has to hit the actual income, right? And now what I do is I differentiate this equation with respect to PL. So if I do that, just using product rule, I'm gonna get here the entry XLR, and here is gonna be P multiplied by this X. Pretty much we have here this quantity here, which is XR with respect to PL, and this should be PL, of course. ML, right? Plus PL partial of this particular good. Here I changed it with respect to the previous time, PL. So we have this, let's do this thing entirely again, okay? So I want to differentiate to PL. So this is a product. So the first thing is with respect to this multiplier. So I have this inner product. So I just take XL. Now the second one is giving me PX as constant. I derive the X So this has in 2 arguments, has of course PL, so it's the first argument, the second argument as before. So here you have the same here as above and the same here as above, okay? So this part is the same object. So by solving this, as this is equal to W, we can just conclude, again, that this multiplication here is equal to 0. So this is equal to 0 here, so I just can rearrange terms. And this is just Walras law here, which is using this notation with products. And now,
Sorry, one above there. The last one, the W prime, P, PD, and then derive in terms of PL.
yeah, the key point here is the following. So is that we want to show that this XL with respect to PL is going to be this combination of the rational PL plus XW of XR, ML minus 1 XR, okay? And then by deriving the income, I'm going to get the same quantity. It kills this XW here. I evaluate that PD, and therefore I'm going to be able to simplify this demand. This income becomes just normal income, and now plugging it back, we get that all this term, which is the Slosky term, is multiplied by ML, okay? So the steps here is just algebraic derivation. So what we're using in this part is just Walras law, and in this part is just the chain rule, and then we just combine these together, okay? So in sum, when I evaluate a PD equal to P, I get that this is equal to multiplying the Slosky matrix times the ML quantity, which is what I told you in this example, right? So what you see locally is this object here, okay? So in particular, you're gonna lose symmetry, and this is the part that I want you to internalize. So it turns out that the Slosky matrix is no longer singular in prices. So the Gavex model is not necessarily satisfy the non-money illusion. So here, individuals may be fooled by increasing income and then doubling prices. These guys may choose differently, right? So these are subjects that are subject to monetary illusion. And in particular, they fail homogeneity of degree 0. They also may not be negative semi-definiteness, and they may fail work. And of course, they may fail also the SARP and the GARP. So in general, this model is not rational, but at the same time, it's not anything goes. So it's a particular model that deviates from rationality in a very specific way. So if you see this Slosky matrix, it deviates with this perturbation, which is this M. So when M is equal to 1, you're rational. But when M is not equal to 1, then the behavior is richer, right? You got a lot more stuff. So again, why do we care? So it turns out that when you model demand, you actually have asymmetric demands, okay? Asymmetric Slosky matrices. So you see this in data a lot. So this model potentially can, of course, explain better data. That means potentially there is a gap between having the potential to explain the data better and actually doing it, right? So again, I have this paper with Nikolai where we actually check this model and estimate a demand function in comparison with a rational model and try to use it to predict out of samples. So using that comparison, we show actually that the Gavex model is better. So looking for attention seems to be actually something that you want to do, okay? But again, Eduardo asked me an important question, and is that what is the relation of M with, for instance, utility or maybe other factors affecting the choice that you have in hand? So in other words, how do I choose attention? So in the end, we want to endogenize attention, right? Because exogenous attention is kind of cool, and maybe it's good for econometricians as well, right? So as I told you, I did a paper using that. So attention is exogenous. So we can just measure it, estimate attention, okay? But if you're a scientist, you also want to understand how attention is formed, do we? So what benefits could come from understanding in economics of understanding attention? So do you have any idea why by reading the text that I sent you yesterday. Why do you think modeling attention or endogenizing attention is important?
From reading the text, you can like minimize dead weight loss for various things like taxes, or it mentions something that if like businesses or whatever know that you're a naive consumer, they can basically exploit you. And so then like the overall well-being, like we're overall worse off.
Yeah, so let me rephrase a little bit two key points, right? So imagine you're a government, right, and you want to collect more money, more revenue by raising a tax. What is the single object of your interest if you're doing that? If you only care about revenue collection, is the elasticity, right? The price, the demand elasticity with respect to price. Okay. So say you want to collect taxes. What's the typical way you can collect taxes that nobody's gonna complain? Like sin taxes, right? So you tax alcohol, you tax you tax tobacco and so on, right? Those are the usual ones, the usual culprits. So you go for them, easy targets. Now, how do you know if you actually are gonna collect what you want? So you need an elasticity, right? So what is the percentage change in consumption of alcohol / tobacco if I raise the price of those items by 10%, right? I now created a 10% increase in my tax. So again, there are many ways that you can estimate this elasticity without knowing a theory, right? That's the first step to do, right? So you can just get a very well estimated elasticity, and that helps you to do some modeling. But what is the issue? So to what extent this price change will depend on actual taste, and what depends on attention. So as you can see from the Zlowski matrix, what you see in data is a mix of the rational object, which comes only from preferences, and the M's, which are come from attention. So the implications of this number, if you are able to break it down into two parts, preference-based and attention-based, are very important. For instance, imagine that you actually are a government that is trying to improve health, right? So maybe you actually want to decrease consumption, not only collect more revenue, right? So then you will care about attention, because a lot of consumers that they are, say you're really rich, and they increase 10% to the pack of, a bottle of whatever you buy, whiskey, right? Are you gonna care if you're super rich and you don't pay attention to that? Not really, right? So then you're gonna be consuming the same, right? More or less. So you're not gonna really change that. So of course you collect a lot of money, and then in your reduce form model, you get Y. But if your objective is really to reduce consumption, then you will actually like to do advertisement as well, right? And say, look, the price of this has increased, don't buy it because so on. So try to make it more salient. So you want actually to decrease that particular thing. Another example of this from real life that people have done it is with the consumption of electricity. So sometimes you hear that, in order to reduce the load on certain peak hours, people increase the price of electricity at certain hours, right? So for instance, in most cities, like the peak hours are around, I guess, from 7 to 10 p.m. So what is a good strategy if you don't want the system to collapse? Is to make it more costly to consume electricity at those hours, right? So in theory, that should reduce consumption. Now, does it reduce consumption? So in most cases, it reduces a bit. So a lot of people are inattentive; they don't care, right? So this is a famous paper. So that was also cited in this behavioral inattention chapter in the evidence. So then, what can you do to actually reduce consumption? So you actually make them aware that price increase. So one way you can do it is by creating nudges to say, oh, by the way, you get a message. Right now, text message, right now, the price of the kilowatt, is this amount, is 10% more. So beware, right? So beware that you're gonna pay more, right? And then, that's, why it's maybe important to get attention. Now, if you're a firm, the same thing, right? So say you want to enter a market and you're trying to compete on price, okay? If you try to compete on prices and then you see that by reducing prices, nobody's buying your good, this is the reduced form elasticity without knowing attention, then you may conclude wrongly that it's just because people don't like your good. But maybe just because they don't know your good is cheaper, right? Maybe they don't know. They don't have information. They are not paying attention to your price. So if you're able to break attention from preference, then you actually may know what fraction of this lack of elasticity with respect to decreasing price, such that your sales go up, depends on attention, right? So yeah, so in other words, finding out attention, measuring it is very important. Now, we may also want to know how attention is formed. So imagine you're a firm and actually want to trying to catch the attention of the consumer. So how people are forming attention, okay? So what do they pay attention to, okay? This almost sounds like psychology, right? So this is a very, this is where things start merging. But we're going to see how economists deal with this problem. So we're not going to model a brain, so that's beyond our capabilities. But we're going to try to still have the ideas of cost benefit, okay? So marginality, cost benefit maximization. So I'm going to start with a very simple first step of trying to tell you the simple problem of Bayesian updating with normal distributions. So it's going to be very easy. And then we're going to think of a model that endogenizes attention. So right now we're going to stop with the consumer problem and study a simpler problem of decision making. So suppose there is a true value, X, right? So X might be a price, but might be other stuff that you want to know, right? X is the true value of the decision that you're facing. Again, an example of such a value can be a price. Now, this object that you want to know actually is random, okay? So it's normal, right? In particular, one assumes for simplicity that is normal. So normally distributed with mean X super D and variance sigma sub X. And okay, so now the agent doesn't know the true value and instead observes a noisy signal, okay? So the noisy signal is the summation of the random variable X plus another random variable epsilon that is as well normally distributed with variance sigma epsilon, okay? So here you see this perturbed version of the value. So in particular, right, think of the price, then you are walking through the aisles of the supermarket, you are not seeing it perfectly. So this perturbation in seeing this thing perfectly is the epsilon. Okay, the same thing with experiment. So the true price is given by the modeler with this distribution, and then the experimenter, sorry, and then use the subject observes S, the perceived price, which is the original price plus this perturbation, right, which is visual perturbation in the example of the experiment. You can imagine other examples, but in particular, S is going to be the noisy signal. Okay, the fact that they are normal is just because we want to make things simple, but in particular, they may have any distribution. Now, I'm going to study this very simple problem, which is that the agent wants to match the state, right? So in particular here, I just want to somehow purchase to match the lowest price or the price I'm finding. So my objective is going to be the distance to the true state of the world. So my action will maximize this utility whenever, if I have perfect information, whenever action matches exactly the state, okay? Now, because I don't know exactly the price, then I'm gonna have some noise. So then what do I do in that situation? Well, I can actually do what is called expected utility, right? So what it means is, remember that X is random, right? A is a choice. So, but I don't know exactly this object X. I don't know it. So I only know a signal, okay? So what do I do? Okay, so I can actually try to infer the probability of X given the noisy signal S. How do I do that? Well, one way to do it is by using a Bayesian updating approach, right? So at some point in your life, I think you have faced this Bayes rule, right? So the idea is that you start with a prior probability over something, and then you receive a signal, and then you update the probability of the object of interest, in this case x, conditional on the signal, right? So this is the posterior probability. So in particular, if I solve this problem here, if I maximize this problem here, then it's going to be that the action by the first order condition. So I just solve this. I take the derivative of this object. I can take the derivative inside the integral, which is the expectation. And then it gives me the following rule. It tells me that the optimal action is equal to the conditional expectation of the random variable x conditional on the signal. Now, it turns out that by using Bayesian updating, so I'm not going to derive it here because this is the work of Nail or your previous classes of probability, but this is just Bayesian updating 101. You get the following conditional expectation, which is M. We're going to use this notation because it's suggestive of the attention that we're studying. The signal plus 1 minus M, the mean of the true object. Okay. So again, what is the M? Is going to be is going to be the variance of the true state, so the price, the true price, divided by the variance of the true price plus the variance of the noise epsilon. Okay. So this model is kind of a way to understand the model we just saw before, using the ideas of Bayesian updating. So in this case, now M's are a number that depends actually on the variances of the true state of the world and the signal. So if your price is Gaussian and normally distributed, and then you get actually a signal, which is the true price, plus the epsilon, which is also normally distributed with a different sigma, right? Then your posterior mean is going to be characterized by this weighted average of the, so this is a conditional mean, so it's conditional on S, on the signal. So given a realization of S, you take the mean of the true state of the world, right? And you pretty much move it towards the signal according to M. And M is this given by the variances. So let's play with it a bit. So imagine, for instance, that there is no noise. So sigma of epsilon is 0. So there is pretty much, there is no noise. What happens here? M becomes 1.
Wow.
So now basically and S is obviously equal to X because epsilon is almost sure 0. So that means that this guy becomes perfectly attentive. Now, if I let this thing goes to infinity, right? So the dispersion is huge, there is only noise, then this becomes 0, right? And now this object here only goes to the default. So what is the issue here? You're actually getting to the correct mean, right? But you don't care really about the realizations of the normal. So you may have a really high draw of the Gaussian, a huge price, and then you still believe is the default, right? So you may be very far off. So it all depends on this sigma epsilon, okay? Now, where does the sigma epsilon comes from? And here is the important part. So we want to endogenize it, okay? So in particular, I'm gonna define the value of information. So what is gonna be the problem now is that this agent can now pick how precise they collect information. So the way we are gonna model it is by letting the consumer pick the sigma epsilon. Everyone understand what this guy is doing? So pretty much the model of attention that we're doing is that we have this x plus epsilon here, and then the agent is gonna pick how precise I'm gonna look at x, right? By choosing the variance of epsilon. So in particular, if I choose sigma epsilon being equal to 0, it means that I choose to be super attentive. So I'm gonna learn exactly x, right? And if I choose sigma of epsilon to be infinity, I am telling you that I'm gonna be super inattentive, okay? So I'm not gonna learn anything beyond the mean. Now, So the value of choosing that particular precision is going to be V of sigma epsilon, which is going to be, of course, given the sigma epsilon, this defines the normal, right? A particular distribution with that variance. And then remember, I have inside this expectation conditional on S, and here you see a star. A star is the optimal value of the action already, okay? And then this is a conditional, so it's a random variable still, so it's not deterministic. I need a number. So I need to take the expectation outside with respect to, of course, the distribution over signals, right? And this distribution over signals is going to be, of course, driven mainly by the normal zero sigma or epsilon. And then I'm going to actually add a cost. So what is the problem here? Imagine I'm trying to now maximize my expected value. So the optimal action is going to be super attentive. Because if you are rational, you are fully attentive, then you're going to maximize this value, right? Because the more precise you are, the better you can match the state of the world. But of course, that's the trivial problem. So we're going to add to it a cost, okay?
Victor,
So,
why
yeah.
is it negative half? I forgot, like the expectation of why it is negative, why you have a negative value there?
No, this is just a very simple model where, because there is no budget or anything, you just want to match the true state of the world, okay? So if you were a perfect agent, so what is your action? So imagine this is an auction, right? So it's a double-side closed envelope kind of trading situation. So what do you want to offer as the price to purchase something? You want to offer the actual price, right? They're giving you. So this is, you can imagine that situation. So the model is just illustrative for purposes of trying to get something analytical. But what this agent is trying to do is exactly match the action to the state, okay? So here you're minimizing the distance between the action and the state, right? Max of minus is minimizing so it's just illustrative, right? But it's a very convenient objective that we want to study. So the point here is that given a particular precision, you get the value of the information structure. So the information structure is how precise you are. So this gives you this value V of sigma epsilon. Now, if you didn't have a cost, information is costless, then you will become rational. So you pay full attention. But we have to introduce a cost. So this cost, the only property I'm going to ask to it is that the first derivative is negative. So more precision, more cost. So in other words, remember sigma is variance, right? So the more variance, the less cost, therefore the negative sign, right? Everyone gets it? Okay. And then my model is going to be as simple as this. Max, I'm going to choose now the sigma epsilon, the precision, such that maximizes the net value of information. So B of sigma epsilon minus C of sigma epsilon. Okay. So let's simplify the problem so we understand what's happening. So we were dealing with the XD to some value. Now fix the XD to 0. Okay, so the signal is centered at 0, just to simplify. Now, if I do that, then it turns out that this value of the sigma epsilon is going to be 1 over 2, 1 over m sigma x to the square. When m, remember, was this variable that we already used before, right? So m is this sigma x or sigma epsilon. So of course, m depends on sigma epsilon. And now, so again, we're gonna simplify this a little bit. So here we can define a particular cost that depends, of course, on the sigma epsilon. So let me call it this just sigma epsilon. To simplify. As before, right? To the square. So it's the same object as we were studying previously. And then what cost can I use? Well, here you can actually use any cost you want. So there are a lot of papers about what cost should I use. But here we're back to the world where you can actually start modeling again. So why people use the Cobb-Douglas? Because it captures some interesting features about the data. Here instead, we're gonna now use the idea that we have actually a cost that have some particular shape. This one here, the thing I care is that it's convex, that it has the first derivative is negative. So the more variance, the more costly it is. So for this particular case, I can define in terms of M, redefining everything in terms of M. So as you can see, I can define this object can be redefined by another C that depends on M now. Okay, and this cost here is going to be 1/2 log 1 over M. So you can verify it's convex, the derivative has the correct sign, take first order conditions. This is a particular example, and I get an M that is 1/2 sigma x minus 1. So let's study some implications.
Victor, do we need that half before log? We can do without the half, right?
Well, this is just to, so this is really a choice. So it's a parametric choice. There is nothing fancy about the 1/2. It can be some kappa, okay? It's just to give a nice result. So if let's see, study this M, right? So imagine you have sigma 2 and sigma 1, okay? Now if that happens, then what do you expect about attention? So turns out that according to this model, if you have that the true value is more variable, so the higher the sigma x, you're going to pay less attention here, right? So the smaller, right, you're gonna become more attentive. So the higher the uncertainty, the lower the attention. Sorry, put it wrong. The lower the attention you pay. Okay. So in this particular model, basically, if things are too crazy, right, it becomes too costly to pay attention. So you just tune out, right? So you say, I don't care anymore. I'm gonna pay less attention, right? So in particular, when things are very precise, you pay a lot of attention because there is a lot of value, I guess, to pay attention. So this is the model. The important thing I want you to remember is that, so this is not the only way people can actually decide what attention they pay. But this model is called rational inattention. And basically what it does is models precision, and it has these two stages. So if you remember from the reading, the whole idea here is that psychologists have pretty much identified that decision-making happens in two systems. System 1, System 2. System 1 is the system where people kind of pre-compile the program they're going to use to make decisions, right? So what it means is you're going to create your heuristics, you're going to decide your attention, right? So what we're solving here is System 1. So this is the pre-compiler section, right? So I'm going to decide how much attention I'm going to pay, okay? And then once you have decided the attention, then you go to System 2, and given the attention, in this case, sigma epsilon, you make your decision, okay? To maximize this thing. So right now we're gonna have a break of 5 minutes. So let me just pause the recording. So we're gonna finish this class with a discrimination with rational inattention. So what is the problem? So we're gonna use this model of rational inattention for a model of hiring, okay? So the problem is that you're gonna have a firm, or for instance, a landlord that wants to hire someone or wants to rent the house, right? And then there are two groups that are observable to the agent. That means the firm. And then from now it's going to be firm, right? So the firm, or let's say the journals, right? You have an editor that wants to publish a paper, and then you have two types of authors submitting, two types of researchers. You have red, blue, right? So you have red. And then you're going to know some information about the means of red and blue and the variance, right? So you have prior information. But then you're also going to see their CVs, and then you want to actually, you may find a signal about them, right? And then the true state of the world is the quality of the potential employer, okay? So this is the model, right? So you have two groups that are observable to the firm. You have some prior belief about the abilities of each of these groups. Red people in this case are better than, maybe better than blue people. So this part is there is some relation about the groups. So in the end, we're going to change this according to the model, but the important thing is that there is some bias. So a priori, you have some information that the mean performance of red people is different from the mean performance of the blue people. So then you have to do two choices. First of all, you have to, as a firm, you have to choose how much time do you spend on each CV. So how much attention you pay. And once you have done that, you choose whether to hire or not someone, okay? So an applicant is of quality Q, and firms do not observe that exactly. But if you hire someone of quality Q, they get a payoff of Q, and otherwise you get zero payoff, okay? So initially you see a signal that tells you to which group the participant belongs to, right? So you know the group. Now, these are the beliefs of the firm. So if you're a red applicant, you're going to be distributed with mean QR and the same sigma as the blue participants, but the blue participants are going to have a different mean, okay? And then we're going to assume that there is some bias in the front of ex ante, right, a priori. So QR is less than QB. So for this agent, the bias is that people that are blue are better in the mean than red people, okay, in this job quality, whatever, Q. So if you hire the mean of the blue people, you're gonna get more payoff than hiring the mean of QR, right, of red people. So what's the problem? So you get a signal. So imagine the signal being the CV. Okay, so the CV reveals two things: reveals your group, okay, and then gives you this noisy value about the quality. So you don't see the quality exactly, but you see quality plus epsilon. Okay, and quality plus epsilon gives you the signal, which now we're gonna call it Y. And then epsilon is again zero normal, zero sigma epsilon. Okay, same as before. Everyone gets what we're doing, right? So Q is random. So quality is random. We have a pool of applicants, and then the mean of the blue people and red people is different. Okay, that's same variance. And then once you want to hire in an individual basis, you get a signal, which is the CV. Okay, and then the CV reveals the type. So whether you blue or red, and also gives you this number Y, which is the quality plus epsilon.
Is the variance of the error term same as the variance of the blue and red?
Sigma epsilon is a choice. Remember, this is how much you want to pay attention to the CVs.
Yeah.
Sigma is something in nature, right, in the market. So sigma is the actual variance of the market, okay? A priori information. So this is not thing that you choose. So sigma is a parameter if you want. Sigma epsilon is a variable, okay? Got it?
One quick question so the means QR and QB, is that just the firm's bias, or is that the actual?
So here we're gonna assume here a statistical discrimination, starting with that. So in particular, you are going to have true information about the marginal distribution, right? So that means that it can be the population description, right? So, but now what is discrimination, right? So discrimination means that, for instance, if I were fully attentive, right, then you will see exactly your quality, and then you will be hired according to your quality, right? So discrimination only happens because these guys have costly attention. So therefore they see some noise. And then the question is, if you use the mean of your group, then you are being judged in terms of something that is not a characteristic of yourself, but rather a characteristic of the group. That's discrimination, right? That's the definition of discrimination. You are being a stereotype, right? So you are Q. You can be high, irrespective of whether you're red or blue, you can be very high Q, right? So because of inattention, what will happen is that the firm will see a noisy signal because they choose sigma epsilon to be non-zero. And then you will see imperfectly the quality, right? And because of that, they will, in the end, use also the mean of the group to which you belong to the site, okay? That's the punchline. So let me go through the steps. So everyone understands what's the issue, right? But the main problem is that the firm has a cost of choosing this epsilon. So I need to get again the value of information, and then I need to get, of course, the cost of information. So what is going to be the cost of information? The cost of information is going to depend on the precision of the signal. So this is how much attention I pay to the CV, the time I spend looking at the CV. So again, it's some C of sigma epsilon, and the first derivative is negative. Why? Because the more variance, the less costly, right? If you are more precise, you pay more. So it's more costly to pay attention. You pay more hours to the HR guy. So the important thing is this. So what is the posterior belief after firms seeing a signal? So they're gonna get this Q prime, right, which is the mean conditional expectation on the signal and of the quality. And this is alpha of y plus 1 minus alpha qg, which is already what we derived before, right? So this is the Bayesian updating with normals, with Gaussians. So where you are taking the mean and moving it towards the signal, right? With this shading parameter, which is alpha. We're using the notation here differently, so you don't confound it with the previous example, but it's following the same skeleton. So alpha is sigma squared plus sigma epsilon. So it's the M, the tension, right? We're now gonna call it alpha just because of a different example. But this is after processing information, this is what the agent, the firm is expecting to earn if they hire this person, okay? So what is notable about this? So if sigma epsilon is equal to 0, so you are fully precise, right? Then what happens? This guy is just hired in terms of what? Of the actual quality, right? Because this part doesn't matter, so the group of the mean doesn't matter, and you only choose according to y, but epsilon is 0, right? Almost surely. So therefore, this thing is just your quality. So you're choosing, you're higher or not according to your quality. So if your quality is higher than 0, you're higher. Now, what happens if sigma epsilon is actually infinite? So collecting information is super hard for you, right? Then what happens? So can someone tell me?
Then in this case, you hire people only based on whether they are red people or blue people.
Exactly, right? And it will be full racial discrimination, right? You only, rent this house to people that are, in this case, it was blue people, right? Right? So you don't care who they are. You only get blue people in, okay? Okay. So what is interesting thing is that because this guy, the firm can actually see the group, so they are gonna choose sigma epsilon differently according to the group. Okay, got it? So once the group is revealed, they are gonna choose sigma epsilon differently. So what is gonna be the value? Well, you're gonna hire if this value Q prime is greater than 0, right? So the value of this is going to be pretty much the max. So the expected value of the signal is this max of this quantity versus 0, right? So this is the value. The alpha depends on the sigma epsilon. So this is the value of sigma epsilon, okay? Now, what is the problem? I have to pick the sigma epsilon as before with the cost. The only property I have is that the prime is negative. So now, let me do two types of agents. The first agent is gonna markets. The first market is gonna be what is called cherry picking. So this is, you are trying to hire for Amazon, right? So most people are below the bar, so you're only looking for the very top people, right? So that means that the mean of R people and B people is below 0. So you are just looking for the best people, so that's cherry picking. And the second model I'm going to study is what is called lemon dropping. So this is kind of landlord's market. So most people you can rent the place to most people, right? So both QR and QB are above the bar. So we're going to see what happens in the interaction of these two markets with knowing the group or the identity of the person and then rational attention. So I'm just going to state today in the 5 minutes I have the theorems, and then we can discuss it next class. So in cherry picking markets, remember cherry picking is everyone is below the bar in the mean, so only a few people are above the bar, right? So if you're cherry picking, then actually the worst group, in this case, the group R, which has worse in means, they get less attention. So like an employer like Amazon, if they have rationing attention, they will spend less time looking at the CVs of red people, right? But once they see that, right, what's going to happen is that the fraction of people hired from the worst group is also going to be lower, right? So in particular, you're going to see less the people of high quality when you're doing cherry picking. Why that happens? Because sigma epsilon is smaller, the smaller the group mean. So because remember here in cherry picking, both QR and QB are below 0. So the effect of the sigma epsilon goes in the same way as the QG. So I'm gonna be more precise, the lower the value. So information is collected more precisely. So let's go back to this part. So here you have minus alpha QG, right? So you can see that this has a minus here, and then the term here is dividing. So there is a positive effect. So they have to go in the same direction, right? So if you want to maximize. So information is collected more precisely for R than for B, okay? So in other words, it's more likely that you hire B, blue. So what happens here is that if you have to look at the CVs of someone of group red, Amazon is gonna look more carefully. And if they look to a CV of someone from group B, they're gonna look less carefully. So therefore, you're giving the benefit of the doubt to the people of group B. And this is the clubby thing, right? So first you have someone from MIT or someone from Western, and then Amazon is hiring them. Who do you think they're gonna look more closely to the CV? According to this model, they're gonna look closer to the CV to people of Western, right? And then to the people of MIT, they're gonna look less closely, but because they have a good mean of the group, they can actually benefit from that. So they just benefit from the pedigree bias, right? So they have high mean. So it doesn't mean that you are competing with, you can be better, you are better from Western than the other candidate. But that candidate from MIT just benefits from the fact that the average MIT is better than the average in Western, okay? Do you understand that? Okay. And lemon dropping is actually this is the market of landlords, right? So lemon dropping means that actually the worst group B gets more attention, rational attention versus the worst group. So lemon dropping, higher the group mean, more information is collected, right? And then it's more likely that B gets higher anyway. So it turns out that in both cases, as long as there is some level of discrimination, right? Always, you know, the red group ends up worse because there is discrimination. As long as there is costly information acquisition, there is discrimination. So the only way there is no discrimination is if you have perfect information, right? So full precision, okay? So you don't have it, there is discrimination. And now the nature of this discrimination changes according to the market and other features. So we're gonna check this with more care next time. But the whole thing here is that, so using rationing attention, we kind of learn a little bit more about discrimination than before. But here there's 2 layers to this model. The first layer is that as long as attention is costly, there is going to be discrimination, right? So think of the situation when there is no cost of collecting information. So sigma epsilon is always chosen to be 0, so full precision. Then you just hire the best people, right? So conditioning on the group is completely redundant. The only benefit of knowing the group is when you have imprecise, you have noise, right? Because then you want to condition on the different mean. So the moment there is costly collection of information, you become, you have bias, you become discriminatory, okay? But you see here, this is very interesting, right? Because now, so what is the new deal here? So, you know, there is something called statistical discrimination, right? This model was invented by Arrow a long time ago. And Arrow kind of say, look, you know, as someone asked, The true distribution, in fact, of the population is such that the mean of the red people is worse than the mean of the blue people. And then kind of arrows said, look, so it's kind of almost natural, quote unquote natural, right? That people discriminate against red people because I am using my prior information, right? This model is very different. So it looks superficially the same, but here the precision of the information is a choice, okay? So it's not natural, right? You choose, like Amazon, you know, landlord, they choose how much effort do they spend looking at applications, right? You see? So in particular, what I want you to realize is here discrimination is a choice, or maybe is, you know, maybe it's technologically driven, right? So for instance, it's costly to check CVs. It's time is costly to do it, but also tells you, you know, that this is something you can actually change with policy, right? So in principle, you can improve, you know, information applications, right? Or for instance, you know that discrimination here, even if you don't reduce the cost of collecting information, there are things you can do. For instance, you can say, oh, so the issue here comes because I can condition on the group. So what about doing applications where you don't see the group, right? So double blind, right? Single blind. Like for instance, I don't tell you my affiliation, okay? So therefore, you cannot condition on that, right? So what it means is now because what is going to be the distribution of the population? Because they are normals, right? You have an average of them, weighted average. So you're going to have some weighted average of the sigma is the same, so it's the same sigma. So you have a weighted average of the means, right? And then you condition on that. And then, you know, it becomes irrelevant what group you are. So people can still be lazy and condition on the mean of the total population, but you are not anymore discriminatory, you see? So a simple way to eliminate this is making it blind to what group you belong. So this also tells you this, but more important, it tells you that if you can improve your technologies of screening, potentially discrimination can disappear, right? So I'm gonna stop now the recording.